be defined for the value 0, everything else doesn't matter. So what I'm really doing is I'm basically getting rid of all the stuff over here for the computation of the kth Fourier coefficient, in which case I can just replace this like so as minus infinity to infinity. And now here is the other fact that I'm going to just remind you of. And where do I put that? Okay, I'm going to put that over here. We know that xt delta t dt integral minus infinity to infinity is equal to x of 0. I mean, that's sort of the definition of the Dirac delta for the continuous time. Basically saying that if you take any value of xt, we multiply it with delta t, it's selecting the zeroth value, okay? And so this one turns out to be so this integral is going to be the value of e to the jk omega st at the value t equals 0, which is 1, right? So this is just going to be equal to 1 over t. So all this math tells you that ck, the kth coefficient, is 1 over t. So in fact, all the coefficients are 1 over t. Yeah?
Yeah, when you first use ck, I think you did put t over the e thing.
We didn't put t, sorry, say it again. Here.
No, the right side.
Right side.
More right.
Here.
Yeah, e minus jk omega.
T, sorry. You're right. Yeah, I just forgot to copy j omega s t. Yeah, there's a t over there. Okay. So what do we have? We have that the kth constant ck is just 1 over t, because basically this integral is selecting the function e to the jk omega st when t equals 0, which is 1. Right? Nice. Pops out. So all the coefficients are 1. So what is st? St is just going to be given by 1 over t e to the j omega st. Okay, and that's it. Basically all the coefficients are going to be just 1 over t. All right. So that's good. So now what we do is we say, okay, what about the Fourier transform of this? And I really have to now decide what to keep in this whole mess here. Okay, I can't use the right hand side, right? How far can I go here? Can I go here? Oh, I can go here. Great. Up to here? Okay, that's good. Okay, so let me just substitute ck over here, all right, to say that st of t, so this number this because I'm going to get confused again. This is 1, this is 2, and here we are at 3. St of t is going to be 1 over t, because that's the coefficient, kth coefficient of the Fourier series, sigma k equals minus infinity to infinity, e to the j omega s t. Okay, that's what the result we have so far, and that's what we're saying it is. So now we can compute the Fourier transform of this by saying that what is the Fourier transform? This is an infinite sum, right? And the Fourier transform is linear. So what have I done? I've done the Fourier series, and now I'm going to do the Fourier transform. How to do the Fourier transform? I say, look, I have a sum. It's linear. Fourier transform is linear. I just take each term one by one. I'm just going to add it up, right? That's what the Fourier transform is. What is the Fourier transform e to the j omega st? Well, another fact. So I'm going to put this fact over here. So this is fact number 1. The other fact we have is that the Fourier transform of delta. So basically 2 pi delta omega minus k omega s is going to have the Fourier transform of e to the j k omega s t. So in the time domain, e to the j k omega s t corresponds to in the transform between 2 pi delta omega minus k omega s. That's a fact, and basically this is the frequency shifting. Okay. We say if you shift in frequency by omega s, then by k omega s, then it's like multiplying in time by e to the jk omega st. Okay, and we've seen this in the Laplace and the Fourier with time shift by t naught in time. Time shift by t naught corresponds to multiplication by e to the jk omega t. And similarly, there's a frequency shift over here. Okay, so this is the, again, a standard result. And we can plug this in to say that this now is a bunch of e to the j omega s t. So the Fourier transform for each of these is just going to be nothing more than 1 over t. Okay, so sorry, forget there's a 2 pi over there. So it's going to be 2 pi over t sigma k equals minus infinity to infinity. That's still this thing over here. I'm going to compute the transform each of these over here separately, which is delta of omega minus k omega s. Okay, so what did I do? I took the impulse train, wrote the Fourier series, computed the coefficient, which a little bit of I guess a couple of mathematical tricks, if you will, tells me is 1 over t. That allows me to write the impulse train as 1 over t times this. This is the Fourier series expansion. And now I'm taking the Fourier transform term by term by looking at the fact that this value over here by the transform table corresponds to 2 pi delta omega minus k omega s, which is the fact I wrote over there. Okay. So far, so good. So at this point, we notice that this is omega s. So this is, by definition, omega s is, if I write that down, omega s is 2 pi over here. This is another fact over here. That's fact number 3. Omega s is 2 pi over t. So this is omega s. So the transform is going to be equal to omega s sigma k equals minus infinity to infinity delta omega minus k omega s. Okay, so this is the, so we'll just write this like this. St of t corresponds to this, the Fourier transform. Okay, so we are slowly making progress. What we've shown over here is that the Fourier transform of s of t is this thing over here, omega s delta k minus omega. What does this look like? Okay, what does this look like? There's a bunch of deltas, okay? And what is deltas looking like? Well, remember delta of t minus t naught is delta shifted in time to the right by t naught, right? So delta of omega is going to have a value at 0. So this one is going to look like this. We have on the omega axis a delta at omega equals 0. And then we have the spikes at omega s minus omega s plus omega s minus 2 omega s plus 2 omega s, etc. Because it's a bunch of deltas. So compare this function, omega s delta omega minus k omega s, with this function, st is delta t minus nt, right? This one over here is the Dirac-Combe, like this, which is all these impulses spaced t apart. This is plus t, minus t, etc. And what we've shown is that the impulse train in the time domain corresponds to an impulse train in the frequency domain, where the time value t gets transformed into the frequency value omega s, which is 2 pi by t. Okay, and there is a multiplicative factor omega s, which it's a constant factor. Okay, it's a scale. But what we're saying is impulses go to impulse trains go to impulse trains. Okay, that's this thing over here. So it's a very nice symmetric result. So we talked about the fact that the transform domain preserves certain things. For example, and I hope you tried this at home, the Gaussian function e to the minus t square is preserved by the Fourier transform. So the transform of a Gaussian is a Gaussian. And here's another one. Transform in time domain, it's a series of impulses in the time domain, which looks like this, spaced by t. It's a series of impulses in the frequency domain, spaced by omega s. Okay, and here we have the expansion contraction going on. If t is large, what does it mean? It's sampling very slowly. Sample, we sample, we sample. It's very slow. Omega s is 2 pi by t. So omega s is going to be small. So the frequency of sampling is low, right? But if my period of sampling is fast, omega s is fast. So if period of sampling is smaller, omega s is larger. So I can say I'm sampling faster. So if I say it's equivalent to say I'm sampling every 10 seconds to saying my frequency of sampling is essentially 1 over 10, okay, 2 pi over 10. Whereas if I say I'm sampling every microsecond, my frequency of sampling is 2 pi times 1 megahertz. Okay, 1 microsecond is 2 pi megahertz. So we get that. And so it sounds obvious, and it is obvious actually, but at the same time it's kind of interesting that we have this change from time to frequency. And when we, in a few minutes we'll see that this is where all this aliasing thing becomes important. But so far, all I've done is to compute the Fourier transform of the impulse train. Okay, so I'm going to walk through this one more time just to make sure everybody gets it, because as I said, this is a place where it's easy to get confused. So we start with this. ST is this one over here. It's some of these deltas over here. So first I'm going to say, okay, I have a periodic function, so I can write it as a Fourier series. Okay, I can do the Fourier series, and this is the definition of Fourier series. All I have to do is compute the kth coefficient ck. And by definition, so these two steps are by definition. I haven't done anything interesting here at all. The only interesting thing I've done, actually, or the two interesting things are to say that, okay, what does ST look like? I'm substituting over here. So that again is by definition just plugging in the value of ST over here. And then what I'm saying is that, look, what's happening is that in this range, minus T over 2 to T over 2, I've erased the wrong thing over there. So in this range, minus T over 2 to T over 2, delta T, everything drops out except the value of delta at T. Everything else goes away because all these other values are going to be non-existent. And then because this range, delta T only has a single value, I can just expand the range. And expand the range at this point, I can essentially, this is all the math I've done, is to go from this to this. Okay, that's really all I've done. And now I just invoke my definition over here to compute Ck as 1 over T. If I compute Ck as 1 over T, then at this point I get St as 1 over T this. Now what is this? This is nothing, it's exactly this over here. All I've done is substitute for Ck. Haven't done anything complicated here. And then I use the other fact being that the time domain e to jk omega st corresponds to a frequency shifted omega in the transform domain. This is again a standard result, and that allows me to plug and get this value over here, and I get this over here. So when you see it step by step, you see there's basically just two definitions I'm using. One is definition here, this is the other definition over there, and the definition of Fourier series, definition of, and this observation that we can transform this integral into this integral. And at this point, basically, I've got this nice result that the Fourier transform of a pulse train is an impulse train in frequency space. Okay? So far, so good. All right, let's step back 1 minute and see, why did I do this in the first place? The reason I did this in the first place is because I want to use this over here. I want to take this product, xt multiplied by st. All right, I want to multiply these two guys over here, and I'm going to use the convolution of the Fourier transform xt and the Fourier transform of st. Right? But what is the Fourier transform of st? Well, now I can finally plug it in, because the Fourier transform of st is going to be this, omega s, this. So let's just plug that in over here. So this is omega s, sigma k equals minus infinity to infinity, delta omega minus k omega s. So I've got one part of it anyway, right? But what is the Fourier transform of this guy over here, xt? Okay. For the moment, I don't care. Okay. For the moment, I don't care. What I say is that I assume that I'm given the Fourier transform of xt as being x of j omega. Let's say I'm given that. Okay. Whatever it is, because xt is this essentially arbitrary function, right? Because it's this virtual function which matches x and t at the right points in time. So let's just call that x of j omega. So that looks like this. right? And it's x and not x tilde because this is the Fourier transform of a continuous time function x of t, not x n t. It's a Fourier transform of x t. Remember, I'm doing the right-hand side, not the left-hand side, right? So I got the x over there. Okay, so what does this look like? We can do one simplification anyway, just because it's so easy, is that we know that omega s is 2 pi by t, right? Over there, omega s is 2 pi by t. So basically these two pi's cancel out. So anyway, we're going to get that out of the way. And so this is going to be 1 over t sigma k equals minus infinity to infinity x j omega convolved with, and this is in the here, convolved with delta omega minus omega s. Okay, so that's the Fourier transform of x and t. Almost there. We're almost there. Any questions about this? Okay, again, all I'm doing is plugging in. Yeah. Okay. Why? How can I move the infinite sum of the convolution? Okay, so basically we're convolving. Yeah, that's a good question. Okay, let's think about it for a moment. So basically we're convolving a bunch of deltas, right? So the convolution of this is going to be, I can tell you, I'm not going to prove it to you, I'm going to tell you intuitively what's going on. Remember, the way we do the convolution is that we take the function value and kind of sweep it past, right? The deltas are essentially standalone. They have no relationship with anybody else. It's just even though it's written as a sum, it's a bunch of separate impulses, okay? I can take each impulse, sweep it, and then sum it up, okay? That's really what I'm saying over here. So I'm not proving it, but I'm telling you intuitively what's going on. So yes, that's a good step. You know, I'm kind of skipping that and saying, yeah, well, it's obvious, but you have to prove it. But it can be proved, and it is a mathematically valid thing, and it's only because it's a delta function. Okay, but yes, that is a good thing to catch over there. So what I'm going to do is to now give you some intuition of what this means. Okay, what this means over here, because if you understand that intuition, then everything will become very, very clear. Okay, and I'm going to explain to you the intuition, and to do that, I have to finally erase some stuff here. Okay, because I don't actually need this anymore. I was keeping this around because I wanted to show you this part over here, so I can erase this stuff here. And now we finally get into the beauty of the transform domain by understanding what is the delta function doing when you convolve with it. Okay. So the fact I'm going to start with is that xt, we can write this, xt equals xt convolved with delta t. Okay, and that again, that just kind of basically is by definition. We actually studied this. I think I wrote this down for you some lectures back, but this is, if you take xt and convolve it with delta t, what you're doing, if you remember the discrete convolution case, what we said was that the discrete convolution, we're kind of sweeping with that value 1 across all of xt, so we can add it all up together and we get xt back, right? So convolution in the discrete time of a discrete function with the discrete delta function gives back the value of xt. That's what we said, and I said that the same thing is true for the continuous case where the convolution of xt and delta t gives you back the original value. What about if we change this to t minus t naught? So if you take xt and we convolve it with delta t minus t naught, it turns out that we get x time shifted by t minus t naught. So we take the whole t and we kind of time shift it, and we get that. Okay, and this we can it's sort of easy to prove this as well, but we can again think of it as we are taking xt, which is some function of time, okay, and then what we're doing is we're kind of convolving it with this time shifted selector, delta t minus t naught. When we do the time-shifted selector, we essentially get the same function, but it's going to be moved in time by t naught to the right. Okay, so I'm going to sort of state it as a fact, and if you want, you can look it up or prove it. Easy to do. Same thing is true if we do it in frequency domain. So if we take x j omega and we convolve it with delta omega minus k omega s, okay, what you're going to get is basically we're going to get x of, or maybe I should just, well, yeah, I'm going to leave out the j for now because it's just a function. Okay, it's going to be basically omega minus k omega s. And this is, what I'm saying is if the transform looks something like this is now omega, and this is x of, okay, omega. Then by convolving it, I'm going to basically get the thing shifted to the right, and this shift over here is by omega k omega s. The k is some integer, right? So what it's doing is, what we're saying here is that, and all we're really doing over here, by the way, is just is substituting t and omega, right? We just can substitute because it's just formal parameter. We don't really, it doesn't really changing anything. Okay, I can put omega here and omega s here, or k omega s here, and this is going to be omega, and this is going to be omega minus k omega s. Right, so I'm just substituting, okay, and delta operator, it doesn't really care whether it's a function of time or frequency, it's just an operator, right? So at this point, what I'm intuitively suggesting to you is that the convolution of a function by delta is shifting it by this value over here. So if you go back to this one on this side, what we're doing here is that we have a sum of convolutions. Okay, a sum of convolutions, and each individual one is taking the value x j omega and essentially replicating it with this, there's a k omega s over here, with this frequency spacing of omega s. Okay, so let me actually draw it, and it will become hopefully a bit clearer. Let's say that we have this to be x j omega. Okay, it's something, and let's say that this one is omega s minus omega s plus omega s. What the convolution is doing is that it's basically going to shift this whole thing like this, and it's going to create these copies, okay, where you're shifting this whole thing to the right, okay, by omega s. So am I doing this properly? Maybe not. Let's make sure I'm doing this right. So they're going to be centered at omega s. So sorry. So let me do this. So just draw it properly here. So there's omega, and I'm going to have, if I have some function like this, then this is going to be omega s. It's basically the center point is shifted omega s. This is going to be 2 omega s. This is going to be minus omega s minus 2 omega s. So what if this thing over here is x j omega, okay, whatever the function is, then this product is this thing over here, where each individual bump was obtained by this convolution over here. Okay, we're frequency shifting by k omega s, and we're summing it all up, and this is what we get over here. Okay, so I'm going to go back to this stuff over here, and basically say that, okay, sorry, I wanted to look at this one over here. If we take the product of two functions in the time domain, we're going to get the convolution of two functions in the transform domain, the Fourier transform with sum multiply 1 over 2 pi. And what I did was I said, okay, let this be some x j omega, which comes from x of t. So x of t corresponds to x of j omega. I got rid of that earlier. But I don't know what that is. It's something, right? But I want to now tell you what will it look like in the transform domain. And the way I do it is to say, okay, this x2 is the impulse train. The impulse train in the transform domain looks like this. It looks like an infinite series of impulses. So impulses in time domain become impulses in the frequency domain. So that's what it looks like over there. Okay. Then what I said was that in the time domain, convolution with delta t doesn't change x. In the time domain, convolution with t minus t naught results in function x shifted by t minus t naught. Okay, by t naught. It's moved to the right by t naught. And in the same way, convolution with omega, with delta omega minus k omega s is shifting it in frequency by k omega s. Okay, it's giving you x of omega minus k omega s, which we can think of as having the function, the transform xj omega shifted. Okay. Okay, so far so good. So two things are come out from this observation. The first one is that what did I start out with? I started out with x of t. Okay, this is my x of t, or I should say I started out with x of nt, which I kind of said is equivalent to x of t st of t. So I have some discrete function. I view that as the product of x of some continuous function with the sample train. And this continuous function has the Fourier transform, x of j omega. Okay? And now what I'm saying is that this product is essentially a replication machine. Okay, it's like a photocopying machine where you take x of j omega and you just replicate it in infinite space. But how did I do that? Okay, what I did was, what I'm saying is that by taking this x of by just sampling x of t, if you start with this over here, x of t, the act of sampling with the impulse train is equivalent to infinite photocopies in the frequency domain separated by omega s, which is 2 pi by t. Okay. So I take some function. Okay. So let's start with x of t. I take some function x of t, and I'm going to sample it. I'm going to get the sample values like so. I'm going to get x of nt. Okay. So here I'm saying instead of starting with x of nt, let's say I start with x of t, right? And I create x of nt from it, which is this stuff over here. And think of these as voice samples, for example. Okay. If I know this x of j omega, then this guy is going to be x of j omega replicated over and over and over again. That's what I showed so far. Okay? And you can work through all the math, other than the one thing that Daniel pointed out, which is how can I get the summation outside, which I've admittedly waved my hands about. Everything else is pretty clean. Okay? So we can finally see what's going on. What's going on is that the act of sampling xt, the continuous function xt, is causing us to replicate its Fourier spectrum over and over again. So what if we want to recover? What if we want to recover x of t again after sampling? Okay, let's say for some reason I'm going to not send you xt, I'm going to send you xnt, and it's Fourier transform, like so. I've sampled it, and I want to say, okay, give me back the original x of j omega. Everything is fine if this is like this. But what happens if I have another situation like this? Let's say that x of j omega looks like this. Let me be more precise. So I have something like this, okay? And let's say that omega s is over here. And this is minus omega s, okay? So I need my yellow chalk again. So this is very complicated. So what's going on is that this center point is going to be moved over here, because that's what happens, okay? This curve is, by the way, xj omega. Okay, this guy is going to be moved over here, so we're going to look at the center point. So it's going to be looking something like this. Okay, Okay, that's what it looks like over here. So we see that this part, okay, in the frequency space, this part over here, the frequencies are overlapping. In frequency space, we have overlap. Okay, so if I were to send you the convolved output, I can't extract from it the original xj omega anymore. It's gone. Okay, and so the other way of putting it is that if this is going to be, let's say, omega L, and this is minus omega L plus omega L, so this width is 2 omega L, okay, and L stands for the largest frequency, okay, of the xj omega, okay, so I have some support. As long as this support is not going to be leaking across when I replicate it like this, okay, all I need to do is to take one chunk, any one chunk of this, like this, or even this, and in frequency space, and then I can extract x of t from it. Okay? Yeah?
What's the problem with the overlap?
The overlap is that now these got to add up, right? So the sum is, when I do this summation over here, I have the replicas, and so the value that's going to be over here is going to be something like that. It's not the individual. I can't just do a band pass. Okay, what I'm going to talk about is a band pass filter. So this is the frequency space. What I'm saying is I sample it. By sampling, what happens is that xj omega is replicated infinitely in all frequency bands. But I can put a band pass filter which says ignore everything here, ignore everything there, and just send one frequency band over here. And from this frequency band, I can actually extract x of t by doing the inverse Fourier transform with no change. The only criterion is that omega s should be greater than 2 omega L, where omega L is the largest frequency component in the signal xt. Okay. So this is called the Nyquist rate. Okay. So I've hopefully given you some kind of intuition about what's going on, and what I'd like you to do is to go back, read through it, because there's quite a bit of machinery going on underneath. Each step individually is relatively straightforward, but the final result is still quite surprising. And I'll give more information about the Nyquist rate next time, and we'll talk about discrete Fourier transform and fast Fourier transform and Z transform, I guess, next time. Okay.